Okay, so welcome to the first experiment on the Theromo-Fluids lab. So today we'll talk about two experiments. The first one will be centrifugal pump. So it's a little bit of history how the invention of pump happened, and in the earlier age, people used counterweight to displace water to take water from point A to point B. But now we have a lot of different electrical methods to do that. And there are different types of pumps, centrifugal, positive displacement. These are the big two types, and they have, like, each of them has several types under them. I'm not gonna go through all of them, just to give you guys a little bit of visual on how they work. So pretty much as you know, that what pump does, it moves liquid from point A to point B, but the method of moving the liquid, it varies from pump to pump. For example, centrifugal pump. Okay, before getting into centrifugal pump, the positive displacement pump, what does it do? What it basically does, it displays itself, not itself, it displays let's say a part of its whole machinery. So it changes the space between them, and in the process, it moves liquid from point 1 to point 2. For example, if you take a look at this one, this progressive cavity pump, it's a positive displacement pump. So you will see that this fluid is moving into a positive direction, and the method is to squeezing the space in, and then making some space in another point. So basically, you're just changing pressure. The differential pressure is what's moving the fluid. However, for the centrifugal pump, it's a little different. It doesn't move liquid with pressure. Rather, it uses its kinetic energy. You see in the middle, there's a little turbine kind of thing that's rotating. We are rotating it with an electric power, and that thing is getting a kinetic energy from the electrical energy and putting that kinetic energy into the fluid and moving this fluid into a path. So this is just another cross-sectional view of a centrifugal pump. I think the picture explains a lot. So there's a common misconception about centrifugal pump, is that these little blades, these gaps, they kind of like cup the water and they take it up, and then they put it, they they let it out. There's another misconception, is that there is a huge pressure drop in here. So that pressure drop forces the liquid to move from this point to here, and then still the same pressure, it moves the fluid from this point to here. But that's not how the centrifugal pump works. Basically, the way it works is that liquid, let's think of it as a liquid ball or a particle in the liquid. Something has to push that particle in here, in this central hub. And the central hub is moving at a speed with a kinetic energy. Then it's gonna take that particle, and it's gonna put that kinetic energy in it, and it's just gonna throw it out with that similar kinetic energy. No big pressure drop in here. Does it make sense? Any question? All right. So once you're clear how this thing works, let's look into the phenomena, the characteristics that centrifugal pump brings. First of all, what are different setups that centrifugal pumps have? Okay, before getting into that, I think Carlos has a question. He's asking, so the blades scoop the water? Uh, he corrected himself. No, the blades don't scoop the water. The blades don't scoop the water. The blades don't create a vacuum or pressure drop. No, it doesn't do it. What it does, it just puts a kinetic energy in there, in the fluid. That's how the fluid moves. All right. So basically, what the centrifugal pump is made of, it has pipes, it has valves, etc. Definitely, you need to have a motor, an electrical connection, and a sealed bands and pipes, and a fluid flow path. Obviously, whenever we're discussing our real life turbo machineries, we're always assuming that the flow is incompressible because the temperature, I'm sorry, the density is constant, because the temperature, we assume for the simplicity of the calculation that the temperature doesn't change. And if the temperature doesn't change, then density doesn't change. Also, to compress a fluid, the amount of pressure that you need is just not in there. So the assumption, the safe assumption would be incompressible flow that goes through the centrifugal pump. However, another very important phenomena that you need to know about this pump is cavitation. As a matter of fact, this is what you're going to study in this experiment. So what is cavitation? Well, as the name suggests, it basically is some bubble into the fluid. But how do the bubble form? They form because of the pressure drop. Now, I just told you that there is no pressure, like it doesn't create a lot of pressure drop. Then how come these bubbles are forming? Well, imagine that you're in a swimming pool and you're throbbing your hands like up and down, up and down. If you have ever done it, then you would notice that when you're putting your hands up from the water, there will be some bubbles on the surface of your skin, because when you're pulling up your hand so super fast, you're creating a vacuum in there. So you're creating a pressure drop in there. So what's happening when there's a pressure drop in there? Liquids vapor pressure goes down, right? I'm sorry. When there's a pressure drop, liquid has its own vapor pressure. So what it wanna do? It wanna vaporize itself, because it just decreased its vaporing pressure. So these localized pressures, they create these localized bubbles. Now, these bubbles are filled with air, so air or steam. So definitely, they don't have as much inertia as a liquid will have. So by the time let's say there's a couple of bubbles in here, and these blades are moving, right? So by the time this blade will touch it, it won't be able to move. Or in other words, these vapor will not move as fast as a liquid. So this blade is going to hit it with all its speed. So those bubbles are going to burst on the blades. It's going to create a shock wave. It's going to deteriorate the material property. So we don't want it. So we need to find out what conditions, how we can prevent it. Does it make sense so far? Any question? All right. Okay, so before knowing, learning the methods of preventing it, it's important that we understand these two parameters: NPSH available and NPSH required. What's NPSH? It's net pressure suction head. So what's available? If you remember this picture that I just told you about, that something needs to push these water particles into the central, right? So what is it? What can we use to push the particles? Well, we call it pressure head. or NPSH available. So basically what it is, it's the height of the water inlet plus the atmospheric pressure. So that acts in our benefit, but there are friction loss. So, like the bends that you have, the pipe length that you have, that's gonna eat up some of this pressure. And then again, you have the vapor pressure head of fluid. So, well, as I told you that the temperature is supposed to be constant throughout the process, but if you have a high temperature in your fluid, then your fluid can vaporize in a much lower pressure, right? So you have way more bubbles in a hot fluid than a cold fluid. So so this is where the account for pressure needs to be calculated as well. But what is NPSH required? Remember the example, throbbing hand on swimming pool? So you can define how much bubble you're making with your hand movement by calculation. However, for practical purposes, that's a super complicated calculation. You don't want to do it. So what happens that the company, that the manufacturer that makes these pumps, they rotate it at different speed. They rotate the turbine at different speed, and they see for each speed what's the minimum pressure you need to stop the cavitation. So this is what NPSH required. Now let's say you have this centrifugal pump, you're pumping fluid through it, and this is the curve that your manufacturer gave you, that as the flow rate goes up, your required pressure goes up. However, for the available net pressure suction head available, so that's on your hand. Like as an engineer, you calculated how much pressure head or how much water head I need in my system. So let's say you start with here, and still you're holding up, like you're pumping more and more fluid. Over here, your available pressure, it's almost barely making the minimum, right? But after this point, this is where whatever much pressure you need is just not in there, not in the system. So you're going to see a lot of cavitation in your system. So you will get a curve similar like that in your experiment. I'll explain it a little bit more, but just as long as you understand this phenomena, you shouldn't have any trouble understanding this experiment and writing it in your report. Okay, so how we can prevent the cavitation? Well, if we want to prevent the cavitation, we need to make sure that NPSH margin, this gap, is as much as possible. And how we can have it? In NPSHR, or the required pressure, designers have no control, or users have no control. It's how the turbo machinery works, and how the pump works. The only control you have is NPSHA available. So you can increase NPSHA, and by increasing that, you can increase that range. You can get whatever much pressure you need at a certain flow rate. So what you can do, you can increase the height of the water inlet, and you can increase the pressure, meaning this is your positive head. So you can increase it, or you can close it and put it under super high pressure. But usually it doesn't, people don't do it because centrifugal pumps are usually used in an open system. So your fluid is open to atmosphere. So usually you won't have any control over it. So the only thing that you can do, you can use the positive head, or you can use another pump to increase the pressure in the line. But we're not gonna take this route. And so as long as your available pressure is higher or equal than the NPSHR plus margin, then you wouldn't have any cavitation in there. And margin, it's kind of like a safety factor. you don't wanna exactly match the requirements, because anything can happen, like maybe there are some particle that got deposited on the pipe. It's going to increase the friction, so the required pressure is going to go up, so you see cavitation. So it's very important that you always account for the safety margin. So how you can calculate the net positive suction head? This is where we're going to use Bernoulli's equation. So Bernoulli's equation, it derives from the assumption that energy doesn't get destroyed or it doesn't get created. It just converts from one form to another form. So definitely, let's say this is your centrifugal pump, and this is where your whole system is. So definitely, it's important that all the pressure at this point is similar to all the pressure at this point. And Bernoulli predicted that. Bernoulli put that in an equation. What are the forms of energy at point A? You got pressure from atmosphere. It can be a closed entity, so the pressure might go up as well. You have a height. You have a z. So it's important that whenever you are measuring these heights, let's say that's point 1 and 2, it's important that you always measure these heights, all the heights in a system, from a single point of reference. So let's say this is your point 1 and the height is z1. You're measuring from this point, or this center. So definitely, if that's z1 for point 1, for point 2 the height is 0, because it lies exactly on the line of the reference. So this height gives you the potential energy that's stored in a system. The higher a fluid is, or the higher a point is, the more potential energy it has. So you got your pressure, you got your potential energy, and third one is your kinetic energy. So your velocity, however much velocity you're seeing in there. So you add all the energies at this point, and you add all the energies at this point, and the total energy will be similar, same. So this is how you can calculate NPSH available. Just get the pressure on the system, get the heights, and if it's moving at a velocity, get that velocity. And finally, this is all the energy that's stored in here at point 1, but you will not see all the energy, the same energy at point 2. So where do they go? Well, they get lost because of the friction in the pipe, because of the bending. So your the pipe friction, it's your major loss, and the bendings are your minor loss. So you subtract these losses from there, and you'll get whatever energy is available at point 2 or at outlet of the pump. Questions? All right. So if you guys have no questions, that's a simple math. So solve this math in your report, and then upload it. I'm gonna definitely you have your reference in here, but still I would prefer if you solve it by yourself so that you can learn. When you calculate the NPSHA or available, you have the atmospheric pressure, you have the liquid surface head, you have the static head, you have the vapor pressure, and you have the losses. Pierre is asking, what will we be calculating for the lab? I will give you the data, I'll give you the values. You calculate those, but this math, it's a part of your report. It's not part of the experiment, but it's just as an appendix. So you solve it and you attach it with your report. All right, so these are the parameters that you're looking at to get your available pressure. Atmospheric pressure is given, liquid level above the pump center line, it's given. So center line is the reference line that we just talked about. And your piping, it's given. So what's the diameter of pipe, that's given. The length of the pipe is given. How many elbows you have, that's also given. So you have pretty much all your data that you need to calculate it. But just remember one thing, that whenever you do a math, always keep your units consistent. For example, you have over here PSI, but let's say your static head, it's in feet, right? So you need to convert this feet thing into inch. Only then you can solve the math. So yeah, just if you like plug these numbers in here, and you will get your result. Another thing that's not given in here is the friction coefficient of the pipe. So the pipe gives you friction, but different material of pipe, different diameters of pipe, different lengths of pipe will give you different pressure loss. For example, if you have a very rough pipe, let's say you have a metal pipe, you have a much more pressure drop than if you have a crystal pipe or a glass pipe, because they have much less friction coefficient. Then for each elbows or for each couplings, you will have a pressure coefficient. So if you have 2 elbows, so you just multiply that coefficient with this equation in here with the velocity of it, and then you get the minor pressure drop or minor losses. So pretty much that's it. That's everything that you need to calculate it. You just plug them in and you'll get a value. This value is in head, it is in feet. But you're calculating the pressure, and the unit of pressure is in is in PSI or pascals, not in feet. Feet or inch is the measurement of length. So how do they correlate? Well, it's there in the engineering world, it's a standard that you can always express your pressure or however much energy is available to a pump with the height or the length. So 31 feet, it means that this pump is capable of moving a water liquid from ground floor to 31 feet up. Does it make sense? Let's say if I have a 20 feet pump. So what it's gonna do, it's gonna take a fluid particle, it's gonna take the flow, and it's gonna push it up to 20 feet at most, without any loss, without any other pressure ingredients acting on it. All right. So whenever you say a head, make sure what head it is. Meaning the same centrifugal pump, this one can push the water 31 feet out. But if you use a heavy fluid, let's say if you use like tar, definitely it's not going to be able to push it 31 feet. It's going to be much lower. So whenever you are defining the pressure with the height ingredients, with the height parameter, then you definitely define what fluid you're using as well. All right, so now comes a second part. It's the efficiency. How do you calculate it? Pretty much however much energy you're giving it and whatever much energy you're getting out, the ratio of it is the efficiency. So you have like the rho g v naught h. So this is your water horsepower. Rho is your water density, your gravity, your volumetric flow rate, and your height. And you divide it the with the power of the motor of the pump, and that's the horsepower in here. The horsepower can also be derived from this equation, which is omega, the rotational velocity of the pump, and you have the torque in here. So you put all these parameters together and you get your efficiency. Any questions? Pierre is asking, for the lab, will we be calculating the NPSHA? Well, I'll explain that in a bit. You will, but I'll go more in details in it. So before that, what are your objectives in the experiment? Definitely gain understanding of the pump system and the cavitation phenomena. So I explained, but you look by yourself, you research by yourself, try to add as much information possible in your report, relevant information, so that you can learn better. Determine and analyze the pump efficiency. To answer your question, Pierre, this is what you're going to do. The first thing, you're going to define your pump efficiency. So I'll give you a volumetric flow rate. I'll give you some of these parameters, and you have to calculate the other parameters, and finally you have to calculate the efficiency. Then you test it at 5 different impeller velocity. So you will have results, you will have data for 5 different velocities. And you plot the efficiency with respect to cavitation for 5 impeller velocities. You plot torque versus flow rate. And so yeah, like this is pretty much it. Like this is a graph that I'm asking from you. Uncertainty analysis, meaning the data, you see that your calculative data and the data that you're getting from your experiment, they're not exactly similar. They don't match. So there is an uncertainty. There is a percentage of error. So you have to explain why those errors happened, what's going on. All right. These are the experimental demonstration. I will just explain this stuff in words to you guys, but definitely like look into those so you have a better understanding of what's going on. Okay, so we will, even though whenever you're going to design something as an engineer regarding to the pump, your goal is to make sure that you don't make any, your system doesn't see any cavitation. However, for the experimental purpose, we will induce cavitation in the system. We will make sure that we can study them well, and we will find out what conditions make them cavitating. So this yellow thing is your turbine blades, your pump blades, and this is where it's going to take the fluid in, it's going to push it out. This is your outlet. This is your inlet. This is a turbine flow meter. So when the fluid is going to go through here, it's going to rotate, and according to its rotation, you're going to read however much flow rate is going through it. Now, how can you induce cavitation in the system? Well, the similar equation, you reduce your NPSHA and NPSHR margin. So you have to reduce the pressure in your system, available pressure in your system. How can you do it? You can induce friction. One way to do it is using a rough pipe, making it longer, reducing the diameter. But that's not modular. Another way to do it is increasing the minor loss. So this is what we're doing over here. We have this valve, and with one rotation, this valve goes down. And as it goes down, it induces pressure drop in the system. So they're like when it's almost touching the surface, you have a great amount of pressure loss in the system. So you will see these things making bubbles in here, and they will form cavity in the system. So you study the volumetric flow rate at different position for this valve. And you're gonna see you're gonna learn how to connect volumetric flow rate with cavitation phenomena. All right, that's just a close-up look of the experimental setup. Okay, so well, I won't go through like step by step, but in the setup you own motor, so you can control your desired RPM, and you can control those using a LabVIEW code that's built in with the whole setup. The valve that I talked to you about, it's the suction valve. So you open at the beginning, and as time goes by, as you're taking the data, you'll start closing it, and you see at what point you start your system start cavitating. You test the whole experiment for 5 different RPMs, and for each RPM, you see how at what point of flow rate the cavitation happens. So all these data I'll give to you, and you got to do those math, you got to do those calculation, you got to explain the graphs, curves, and that's going to be your report. Question? All right. So what are the outcomes I'm expecting? Well, we already talked about it, but make sure that you answer all these questions in your theory section. All right. So in your theory section, in your introduction section of your report, I'm expecting a lot of theory, a lot of discussion on turbo machineries, and your result and discussion section, I'm expecting your maths, your calculations. So yeah, you can use this. You can answer these questions, and based on those, you can write your report. All right, that's it for the first experiment. I'll give a pause. I'll ask you guys. Okay, so this is the second one, and we're gonna talk about thermofluid heat conduction for the second lab. What are you gonna do over here, and what's the principle of heat conduction? So conduction happens when you have a solid, and what the goal, the objective of this experiment is to calculate thermal conductivity of a material. So I might or might not give you the name of the material. So you calculate the thermal conductivity, and since thermal conductivity is a material property, so if you look online, you should be able to find what material it is by measuring the conduction. And then we will study the implication of a Fourier rate equation. Fourier rate equation is an equation that kind of like calculates the heat transfer rate for you. Okay. Comes to the basic, what is the first law and second law of thermodynamics? So the first law of thermodynamics, it derives from from the energy conversion law, that energy can be created or destroyed, just transferred from one form to another. So your total heat in you can describe it like that. Like, let's say if you have a system, a gaseous system, and you put it under heat. So however much heat it's getting in, it's going to be equal to the amount of its the work done by itself, and the total amount of internal energy increase. All right. However, it doesn't tell you what direction the energy is going to go, what direction the heat is going to go. Meaning, if you have a gas balloon in here and you put it in a very hot environment, so is the heat going to come from outside to the gas balloon or from the gas balloon to the outside? So that's when the second law of thermodynamics comes into action. It tells us that heat always moves from hot environment to cold environment. So if your air around the balloon if it's hotter than the air inside, then definitely heat is gonna go from air to your balloon. If the other way around, then the heat is gonna go from the balloon to air. There are different mechanisms of heat transfer: conduction, convection, and radiation. Already talked about conduction. Conduction happens when one substance. When heat moves from one substance to another by direct contact. Convection happens into a fluid, so it doesn't. But it's not metal; it's a fluid. However, when you have a metal surface and you have a liquid surface touching each other, the heat transfer, we also call that convection. And then there is a radiation. It's ubiquitous. It's all around us. Solar radiation, we know. Whenever there's a flame, you can feel the heat. Even when you're standing a little bit far away, that's called radiation. The method, the way of moving heat without any medium. So that's your Fourier's law that we have talked about. The Q conduction, meaning the amount of heat being moved by conduction, equals to A, the cross-sectional area. So let's say your heat is moving from this surface to this surface, then your cross-sectional area is going to be this one. So the bigger the cross-sectional area is, the more heat can flow from one surface to another surface, right? So don't confuse this surface with this surface, because this also accounts for the heat transfer, but that comes as a length. So the distant these two surfaces are going to be from each other, the lower the heat transfer rate is going to be. So to sum up, the equation looks like that. The amount of transferred heat from surface A to surface B is proportional to its cross-sectional area. The higher the area, the more heat transfer. Proportional to the temperature difference. The higher the temperature difference, the more. So if you have 100 over here and 0 over here, and if you have 200 and 0 over here, definitely for 200 you'll see much more heat transfer rate. And that's pretty common sense. As the length goes up, the amount of heat transfer rate goes down as well. So you combine them, you still need a constant. You still need a constant to fully define this equation, and this is where the constant comes in. So this is an intrinsic property of metal, and this is conduction. This is what you're calculating in your experiment. You might ask why there is a negative sign. Well, it's because you're getting the difference of temperature. And so what you're doing, you're subtracting the initial phase from the final phase. So you have one surface TB over here and you have TA over here. So you subtract TB from TA from TB, because TB is the final stage. However, you know that TB is smaller than TA, so this value is going to get negative. So if there is no negative sign in here, your conduction will be negative. So that will tell you that will give you a wrong sense of heat transfer direction, heat transfer amount. So you need to have a negative sign in here to make the whole thing positive. All right. Questions? Okay. Then comes the thermal resistance model. You all are familiar with the electrical circuit and this equation. The amount of electricity is proportional to the amount of voltage difference, and it's inversely proportional to the resistance. We can use the similar analogy in thermal resistance model. So the amount of heat transfer is proportional to the amount of temperature difference and inversely proportional to the resistance. So if you know the Q, if you know the del T, you can figure out the R. Or the other way around, if you know the R, you can get this too. So what do the R account for? So you know that Q equals to del T over R. And then from here, you know that Q equals to negative Ka del T over X. So if you compare these two equations, your total resistance looks like that. Your resistance, like the higher your length is, the more resistance you see. It's common sense. The higher your area is, the less resistance you see. Also, it's the same thing, right? The Fourier equation. The higher your conduction capability is, the lower your resistance is. So what conductivity tells you is that it's the capability of a material to move heat from point A to point B, and how smoothly, how fast it can do it, or like the more conductivity you have, the more heat transfer is possible in the system. You're gonna have to use this equation in your experimental report as well. Okay, so this is how your whole system looks like. That's a cylinder, and it's made of a bunch of little tiny cylinders. These are these tiny cylinders. So your whole system is made with 10 or 8 of these little tiny cylinders. Now, all the other cylinders, except one, we know what material they are, we know what conductivity they have. But these three, we don't know. So what we're gonna do, we're gonna put this in the middle section, and we're gonna calculate the heat transfer, we're gonna calculate the temperature difference, and from there we're gonna find out what conductivity this specific metal has. And from there we're gonna find out what metal it is. These extruded things are your thermocouples. They are connected in here. So this screen will tell you which thermocouple has what value. You have 10 thermocouples in total, but only 4 and 5 are the thermocouples that's going to get into that unknown material. So the way you have to calculate it, you have to calculate it step by step. Meaning, if this cylinder is made with 5 smaller cylinders, 10 smaller cylinders, and you know 9 of them, then you have to go from 1 to 4, the known material, then you put this in, you get the 5th one, and then from there downwards. And you also need to have a temperature difference, right? You need to have a hot temperature on top and a cool temperature on bottom. So this system gives that one as well. You guys can see that pump on that side, and this is the water pipe. So you have a water cooling system in your setup, and the electricity. I don't know if you can see the the wires coming from here, these black wires from the back, from the same setup. Through these wires, you can control the electricity that's getting into the system. So as I told you, the energy cannot be destroyed; it can be just converted from one form to another form. So the heat that you're getting in there, the Q, this is the electricity that you're getting. So if you have 10 volts in your system and 1 ampere, power that you're putting into the system is 10 watts. So you can safely assume that you're putting 10 watts of Q in your system, and this fluid system, it's capable of taking out, I wouldn't say 10 watts, but somewhere. So you have a great temperature drop along the system. It will become more apparent, more clear once you see those data. All right. So I already explained this. This is the schematic of the whole setup. Uh, just take a look and let me know if you have any question. All right. So these are the sample experiment videos. You have to go through them, and this is the equation that you have to use. So we already explained everything that needs to get into the calculation. And what I'm expecting in your result, definitely a plot of temperature versus distance. Then definitely calculate the thermal conductivity for different specimen. Identify the what material it is. Calculate the percentage of error. So what is that? Well, you know that you are putting 10 watts in your system, but when you account for all the heat in your system, when you go block by block, you know the del T, you know the R, you can calculate the Q for each system. You will see that there are the value don't add up. And why is that? What could be the reason? I'll let you take a stab at it. Write down your reasons in your report. And finally, use the thermal resistance model to calculate the heat loss. So that's pretty much it. What questions do you guys have? Um, okay, so before getting into the question and answer session, let me stop the recording.